Well, I would like to welcome today Dr. Phillip Lancaster. Dr. Lancaster is a clinical assistant professor in the Beef Cattle Institute. He received a Global Food Systems Seed Grant Award in 2021 for a project titled Enhancing the Economic Value and Business Viability of Food Waste to Animal Feed Conversion. Dr. Lancaster?
All right. Thank you, Maureen. So, food waste is a challenge for sustainability of our food production systems. Greater than 40% of the food produced is wasted in some shape or form, 50% of which is disposed of in landfills, which is the third largest anthropogenic source of methane in the U.S. However, more useful purposes are within reach. Here, looking at the food recovery hierarchy on the right, we can see that landfill or incineration is at the very bottom of the list and is the least preferred disposal form of food waste, where composting, industrial uses, feed for animals, feeding hungry people, and reducing the volume of surplus food generated are better options for use of food waste. But not all food waste can fit in all of those categories. And so the best use for a lot of food waste is to feed animals. So currently, through the food production system at the industrial processing step, about 5% of the waste goes to a landfill, whereas 80% of that already is diverted to animal feed. But at the retail level, about 45% of the food waste goes to the landfill and only 12% goes to animal feed. And then at the restaurant level, and even probably at the home or private individual level, 97% of food waste goes to the landfill, whereas only 1% goes to animal feed. So humans have fed food scraps to swine and poultry for centuries, but more recent regulations require heat processing or even ban feeding food scraps for food safety concerns. But cafeteria food waste can be an adequate replacement for corn and soybean meal in swine diets from previous research, but little research has been done in poultry diets. The biggest concern with using food waste in animal diets is the variability of nutrient density. The coefficient of variation for individual nutrients is often greater than 100%, which provides a lot of difficulty in consistent diet formulation and/or animal performance. Additionally, food waste has to compete with other feed commodities on a cost per nutrient basis, primarily corn and soybean meal. But food waste has a very high moisture content, and so that means that we either have a short transportation radius from the center of origin of the food waste, or we have a very high drying cost to be able to transport that food waste longer distances. And so there needs to be a value added proposition to increase the economic viability of converting food waste to animal feed. Astaxanthin is a powerful antioxidant, anti-inflammatory, and antimicrobial molecule. There's synthetic astaxanthin is used in poultry diets currently and is very expensive. And we think that astaxanthin has the potential to reduce the prevalence of foodborne pathogens in the food production system. And so food waste could be a substrate for yeast fermentation that produces astaxanthin, and we end up with an astaxanthin-rich feed product to use in animal feed. And additionally, yeast cells can improve gut health in livestock, but this has not been tested. So our objective was to develop processes, products, and decision tools to increase diversion of human inedible food waste from landfill to animal feed. We had 4 objectives. 1, to determine the nutrient digestibility of food waste and astaxanthin-rich fermentation product in poultry. To investigate the effect of astaxanthin-rich fermentation product on foodborne pathogens. Number 3, to identify the nutrients with the most influential variability on poultry growth, performance, and astaxanthin production. And number 4, to optimize food waste nutrient content and yeast fermentation conditions to efficiently produce an astaxanthin-rich feed product from food waste. So we collected food waste from the Kansas State University Kramer Dining Center for 30 days from August 16th to September 14th of 2021. The daily food waste was weighed, ground through a meat grinder, thoroughly mixed, and then subsampled for poultry growth and digestibility experiments, nutrient analysis, and yeast fermentation experiments. First, looking at the methods for the digestibility experiments, daily food waste samples were combined to create one composite, mixed with soybean meal and extruded at 140 degrees Celsius. Additionally, the astaxanthin-rich fermentation product was mixed with soybean meal at 15%. And 2 digestibility experiments were conducted, one to determine the apparent metabolizable energy content of food waste, and the second to determine the apparent ileal amino acid digestibility of food waste. So we used 300 one-day-old male broilers that were fed for 20 days to determine the metabolizable energy content, and we collected fecal samples on days 18 through 20. We had 5 treatments in this experiment with a basal corn soybean meal diet, and then we replaced 30% of the basal diet with either conventional soybean meal, extruded food waste, or the astaxanthin-rich product. In the apparent ileal amino acid digestibility experiment, we used 240 one-day-old male broilers that were fed for 21 days, and on day 21, we collected ileal samples from the birds. We had 4 treatments: a conventional soybean meal, extruded food waste, and astaxanthin-rich fermentation product. There you can see the diet formulation for the 2 experiments. On the left-hand side for the metabolizable energy experiment, corn and soybean meal made up the majority of the diets, and especially the basal diet, and then we added 30% of the test product for the other 4 diets. And then titanium dioxide was included in these diets as a marker to determine digestibility. The amino acid digestibility diets are on the right-hand side. You can see the test product was about 44% of the diet, except for the astaxanthin product, which was a little higher, so that we could maintain a consistent crude protein concentration of the diet that you can see there at the bottom of the table. And additionally, the first 5 limiting amino acids in poultry diets are listed there, and we kept the amount of those in the diet consistent. So first here, looking at the results from the apparent metabolizable energy experiment, we can see that the conventional soybean meal and the astaxanthin product were similar, but had a lower metabolizable energy content than the extruded soybean meal, and then the extruded food waste was intermediate. Looking at the results from the amino acid digestibility trial for the 5 first limiting amino acids in poultry diets, we can see that the conventional soybean meal, extruded soybean meal, and extruded food waste all had similar amino acid digestibility for each of the 5 amino acids. However, the astaxanthin product had lower digestibility for each of the 5 amino acids. For our second objective, we were looking at the effect on foodborne pathogens. We had a growth experiment with 420 one-day-old broilers, and fecal samples were collected on days 0, 10, and 20. We had 7 treatments in this experiment. We had a basal diet of corn and soybean meal, which served as our negative control. We had a basal diet with commercial astaxanthin that served as a positive control, and also a basal diet with antibiotic that served as a positive control. And then we had 4 test diets, 2 with food waste at a low and high inclusion level, and 2 with the astaxanthin-rich fermentation product at a low and high inclusion level. From fecal samples, we isolated salmonella through enriched culture, which was transferred to a broth and incubated for 24 hours. After the selective enrichment, a loop full of each broth culture was streaked for isolation onto xylose lysine turgidol for auger and incubated overnight. And we also isolated Campylobacter through enriched culture, and then was streaked on for isolation on Campy cephix auger and incubated at 42 degrees for 48 hours. The foodborne pathogen results are still in progress. We just completed this last week on November 11th, and so data analysis is still ongoing. Looking at objective 3, which was to evaluate the nutrient variability of food waste samples, we used daily food waste samples that were sent to Cumberland Valley Analytical Services for chemical analysis of dry matter, crude protein, crude fat, starch, NDF, ADF, and individual amino acids. And then we calculated the mean standard deviation and coefficient of variation, which were compared with corn and soybean meal from the NRC for swine from 2012. We also developed 4 food waste products, one for each of the 4 weeks of collection, that we use to evaluate the variability in the metabolizable energy content and amino acid digestibility, where we used 1-day-old broilers and collected fecal or ileal samples to evaluate metabolizable energy or amino acid digestibility, where similar to objective 1, for metabolizable energy, we had a basal diet of corn and soybean meal. And then for the test diets, we replaced 30% of the basal diet with conventional soybean meal, extruded soybean meal, or each of the 4 food waste products. And then for amino acid digestibility, we compared conventional soybean meal and extruded soybean meal with each of the 4 food waste products. So here is the experimental diets for the metabolizable energy experiment. You see the basal diet there of corn and soybean meal, and then we replaced 30% of that with the test product of soybean meal, extruded soybean meal, or one of the 4 food waste products. And then for the amino acid digestibility, again, here on the right-hand side, the test product was included at about 45% of the total diet, with dextrose making up 50% of the total diet. And these were adjusted so that the protein content and the amino acid content for the first 5 limiting amino acids in poultry diets were consistent across the 6 treatments. So looking at results of the nutrient variability of food waste, on the left-hand side, we're looking at the mean for protein, fat, ash, starch, and NDF of the food waste in gray, the corn in dark purple, and the soybean meal in blue. You can see that for protein, starch, and NDF, the food waste is kind of intermediate of the corn and soybean meal, although the food waste had a much higher fat content than corn and soybean meal and a slightly higher ash content. When we look at the right-hand side and the coefficient of variation for these same nutrients, in general, food waste had a much higher coefficient of variation than samples that had been submitted for analysis and recorded in the swine NRC for corn and soybean meal, with the exception of fat. Soybean meal had a high variability in fat content. We looked at the 5 first limiting amino acids and the mean of the food waste, daily food waste samples. And for the food waste, it was the content for methionine, lysine, threonine, valine, and isoleucine were intermediate with corn and soybean meal. But the food waste had a much higher variability than samples submitted to the swine NRC for corn and soybean meal here on the right, with variability ranging from 40 to 60%. Compared to 10 to 20% for corn and soybean meal for each of the 5 amino acids. Looking at the metabolizable energy results for food waste products across 4 weeks of collection, you see that in general, the food waste products were similar to soybean meal or extruded soybean meal, with the exception of food product 3 being higher than the conventional and extruded soybean meal. And we saw that food waste had a coefficient of variation of about 15% across the 4 weeks. For amino acid digestibility, we see that the food products had a digestibility for each of the amino acids that was somewhat similar to conventional soybean meal, but generally less than extruded soybean meal for each of the 5 amino acids. However, the digestibility of the amino acids were much more consistent than digestibility of metabolizable energy, with a coefficient of variation of only 2.6 to 5% across the 5 amino acids. So for our fermentation experiment, objective 4, we used an astaxanthin producing yeast culture to ferment food waste. Fermentation conditions were evaluated with enzymatic digestion using different combination of enzymes. Here on the right-hand side, you can see that we had a control treatment of just the yeast only, or we had 4 enzyme treatments with either glucoamylase, alpha amylase, proteinase, or viscozyme L, which is a product. And then we also tested solid loading of 5, 10, 20, or 30% food waste in the fermentation. Here, looking first at our enzyme treatments, the results from our enzyme treatments, we can see that the first 3 enzyme treatments had a relatively low production of astaxanthin in the bars here on the left, but the 4th enzyme treatment with the viscozyme had a much higher production of astaxanthin. And you can see that in the pictures on the right-hand side. The darker the orange color, the more astaxanthin was being produced. And so you can see enzyme 4 had a real darker color than the other treatments. And then for our solid loading test, for 5, 10, and 20% here on the left-hand side, you can see across days 3 to 10 that 10 and 20% there was not an increase in astaxanthin production, but with a 5% loading, there was a drastic increase in astaxanthin production. And you can see that as you look across days here on the pictures on the right. The 30% loading, there was so much dry material that there was not enough moisture, and we stopped that fermentation after day 3. So in summary, composite food waste had similar metabolizable energy and amino acid digestibility as conventional and extruded soybean meal. The astaxanthin-rich fermentation product, though, had lower amino acid digestibility than soybean meal and food waste. The daily food waste had similar nutrient concentration as a mixture of corn and soybean meal, but the food waste had greater variability in nutrient concentration than corn and soybean meal, and but it did have similar apparent metabolizable energy and amino acid digestibility as conventional soybean meal, but lower than extruded soybean meal. The enzymatic digestion of food waste with carbohydrate digesting enzymes at 5% solids provided the greatest astaxanthin production. And those enzymes included enzymes for both simple carbohydrates in starches and in more complex carbohydrates. So in conclusion, food waste can be used in poultry diets having similar nutrient concentration, metabolizable energy, and amino acid digestibility as corn and soybean meal, and or as a substrate for astaxanthin production. However, the variability of nutrient concentration of food waste may limit the inclusion level in poultry diets. And here is the contact information for investigators on this project.
Great. Thank you so much, Dr. Lancaster. And I would encourage anyone listening to the presentation, if you've got questions or would like to discuss the project further, please reach out to either Dr. Lancaster or one of the colleagues listed here on his contact information. Thank you.